Cool, so in this bonus video, we're going to prove Euler's identity that e to the I pi is equal to -1. So let's kick it off. And we're going to begin by first saying that I, that is our friend, the imaginary number. And if you haven't seen imaginary numbers before, we're just going to use the following couple properties of I. In that when I squared is squared, this quantity of I squared is equal to -1. When we cube I, as in I cubed, this is equal to -I. And when we take I to the 4th power, well, that's going to be equal to 1. I to the 5th power would then just be I times a 1, because we can break it into I to the 4th times I, and that's just going to be equal to I. I to the 6th power is going to give us a -1. I to the 7th power is going to give us a -I. I to the 8th power is going to give us a 1 again. And we're going to see this kind of cycle keep going between I, -1, -I, 1, and just keep repeating itself. So where we're going to go with this, if you just believe me that these properties of our imaginary number I are true, we're basically going to do an expansion of a Taylor series for the exponential. So let's kick that off. If we look at just I, or e to the ix, we're going to expand this in a Taylor series. So if you remember the Taylor series for the exponential, that's equal to the infinite series from n equals 0 to infinity of whatever's inside the argument of the exponential, which in this case is that I times x. And we raise that to the nth power all over n factorial. All right, so let's check it out. If we just start computing off terms of this series, when n equals 0, we have, well, a quantity raised to the 0th power, which is a 1, divided by 0 factorial. The first term of that series is a 1. The next term of the series we just get is I times x. The next term of the series, if we just write it out, is a quantity ix squared all over 2 factorial. The next term is a quantity ix cubed all over 3 factorial. The next term is ix to the 4th all over 4 factorial. And hopefully you can see the pattern that's going to emerge. Again, just ix raised to the next power of n divided by the next power of n factorial. Okay, so what we're going to do next is just use all those properties of the imaginary numbers to start writing out the terms of those I to whatever powers. Okay. So the 1 is just a 1. The ix, I is just the 1st power, that is just I times x. Next term, we have ix quantity squared. Well, that's an I squared times an x squared. And we saw that I squared is a -1. So the next term is a minus x squared over 2 factorial. All right, let's check out the next term. The next term is an I cubed times an x cubed. And well, an I cubed gives us -I. So this term looks like a minus I x cubed over 3 factorial. Oop, I forgot to highlight that previous I in red. I'm just trying to keep track of where all the i's are. All right, the next term we have an I to the 4th times an x to the 4th. Well, I to the fourth just gives us a 1. So this term is just plus x to the fourth all over 4 factorial. All right, the term after that, we have I to the fifth times x to the fifth over 5 factorial. I to the fifth, well, that's just equal to I. So that's plus I times x to the fifth all over 5 factorial. And now if you're really good, you'll kind of see the pattern. Again, we could keep listing off terms here, but you might notice something special about the terms that have i's and the terms that don't have i's. So right now we're just going to group all the terms with i's and the terms without i's. So first let's collect all the terms that don't have any imaginary components on them. That's the 1, the minus x squared over 2 factorial, a plus x to the fourth over 4 factorial, and we could keep going on. You can kind of see the pattern that looks like it's emerging. We only have even powers of x over the corresponding even n factorial. All right, let's add to that the terms that have i's. And I'm going to pull I out in front of that series. So if we pull I out of every term, well, the second series, when we collect terms, we have an I times x, so we just get an x there. The next term we have is a negative I x cubed over 3 factorial, so if we pull that I out in front, this is minus x cubed over 3 factorial. The next term after that, we have that plus I x to the fifth over 5 factorial. So pulling that I out in front, we get plus x to the fifth all over 5 factorial. And again, we could keep going on if we had listed more terms. But you see in the second series that we're collecting, this looks like x's only raised to odd powers being divided by the corresponding odd factorial. So if we just reflect on that and think about what series are synonymous with only even terms and only odd terms. And well, you can convince yourself that that first series, this is actually what's in blue. That's our pale to cosine. And well, in the second series, what's in those blue square brackets, that's actually our pale sine. So what this actually equals to is e to the ix is equal to cosine of x plus, and this is important, I times the sine of x. So we have this new relationship that we just proved through Taylor series. And once we have this relationship, proving Euler's identity is actually going to become quite trivial. So at this point, we have something pretty cool that we just showed is true, that the e to the ix is equal to cosine of x plus I times sine of x. Now let's hit this with Euler's identity. So recall what we're trying to prove is that e to the I pi is equal to minus 1. Well, we just showed that e to the ix is equal to cosine of x plus I sine of x. So the only thing it looks like we need to do is everywhere there's an x, we just replace that with pi and see what we get. So if we let x equal pi here, we have e to the I pi equals cosine of pi plus I times sine of pi. And you might remember, well, the sine of pi, that's just equal to 0. And well, the cosine of pi, that's equal to minus 1. So therefore, we have that e to the I pi is equal to -1. And we were able to prove this relationship, which is one of the 10 most famous equations in mathematics, using Taylor series.